Why, hello, and welcome to AP Chem video. Hey, you know what? We're almost to the AP exams. Pretty exciting. But anyway, so let's take a look at electrochemistry. So I want to remind you guys about the basics of redox reactions. So we have this really classic redox reaction right here. And I want you guys to remember oil rig. Oxidation involves loss of electrons. Reduction involves gain. There's an oil rig. Looks so pretty. Makes me think of spring break. Or maybe you remembered Leo says grr. Losing electrons, oxidation, gaining electrons, reduction. Whatever. Take a redox reaction, break it up into its half reactions. So this is what we're looking at here. So the zinc is a +2. Sorry, the zinc is a 0 because it's in its elemental state. Okay. And then over here, it goes to a +2. So we're going from 0 to +2. That is a loss of electrons. So zinc solid breaks down into zinc 2+, and you lose 2 electrons. So that's our oxidation. Reduction is, of course, the opposite. So right here, the iron is a +2. And then over here, it's in its elemental state, so it's going to 0. So it is gaining electrons. So that's our reduction. Little terminology that I know you guys don't like too much. The oxidizing agent, that's what's going to cause something else to lose electrons, is what's being reduced. Okay, because by being reduced, by gaining electrons, you took it from somebody else. So therefore, you caused something else, or you are the agent of oxidation. So the iron chloride, so usually you would say the whole substance, not just the iron 2+, for instance. The iron chloride, the whole thing, acts as the oxidizing agent. The reducing agent is just the opposite. It's what's being oxidized. So by losing electrons, you must be giving them to someone else. So therefore, zinc is the reducing agent. We'll try to limit how much we use that terminology, but it's definitely something that you want to get clarified. All right, so that's an easy little recap. Now, this whole reduction potential business. So you definitely want to have your little pink sheet out that looks something like that. Have that out because we're going to refer to it a whole bunch. So just the generals. I'm not sure you guys caught all this in class. So which substance on the table is most easily reduced? So that means it's the best oxidizing agent. So who on that pink sheet wants electrons more than anybody else? So if you take a look at your sheet, all right, well, these are written as reductions. So every one of these reactions is written as a substance gaining electrons. So where is it most favorable? Where is reduction most favorable? And that's, of course, right up here, this top line. So fluorine wants to gain 2 electrons to become the F- ion. Well, heck, does that make sense? Let's see. Fluorine, 7 valence electrons, wants to gain 1 more to become 8. Okay, or if you guys remember back from Chem A, fluorine, the most electronegative element on the periodic table, that kind of implies that it really wants electrons. So if you wrote out the half reaction, it would look something like this. So I'm just copying it from the pink sheet. So F2, gaining 2 electrons, making 2 F-. So of course, fluorine wants to gain electrons. So it makes sense. So positive electron potentials means favorable. Okay, and that was a big, nice positive number. All right, same sort of question. Which substance on the periodic table is most easily oxidized? So who wants to lose electrons? So if you take a look, we're talking about oxidation, so you're going to have to look at that table backwards now. Okay, so if you want to look at it as oxidation, we're looking at it from products going to reactants. Okay, and when you do that, that means these sign changes, or these signs change. So let's see, these will be, if you flipped it, negative, 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 these would all be unfavorable in the backward direction. So you come down here, okay, this guy right here, being reduced, not happy. If you look at lithium metal being oxidized to lithium plus, and therefore losing an electron, if you change the sign, that would be a positive 3.05. So it's very favorable in the backward direction. So if you write that half reaction, that's totally fine, but you do have to make sure that you write it backwards. So lithium solid, okay, breaking down into lithium plus, losing an electron, and there's my electron that's lost. Do you guys think that lithium metal would want to lose an electron? Well, I think that's a property of all the alkali metals. Okay, they have that 1 valence electron in their elemental form. They want to get rid of it. Okay, so metals in general like to be oxidized. They like to lose electrons. And if you look at that at your pink sheet, I think you would see that supported. Okay. Okay, so a little bit more complicated. This question says, circle which of the species in each pair is a better oxidizing agent. Okay, so that means it wants to be reduced. I'm just going to tell you right now, when you compare these, please, make sure you write down the numbers so it doesn't get confusing. So what do I mean by that? Let's say if you guys look at NO3 minus versus I2. Now, we are asking about things that want to be reduced, so that table is written as reductions. So we're going to look at the table as is. So let's see, this one, I believe I did it in black. So let's see, there's NO3 minus being reduced to NO2 or to NO. Okay, the potential for that is a positive 0.96. We were comparing that to I2, which is down here a little further. I2 gaining electrons to become I minus. The potential is 0.53. Okay, so who's more favorable? More positive wins. So the nitrate ion would be a better oxidizing agent, or wants to be reduced more. Okay, so go ahead and take a look at A, B, and C, and try those out. So if I were you, you probably already saw the answer. I know how you people work, but I would stop the video and really look at your pink sheet and see if you can figure these out correctly, and then check your answers. All right, so let's see, manganese 2 plus versus MnO2. So if you find that on your list, let's see, the Mn2 plus is over here. So it's favored, it's not very favorable, negative 1.18. Mn2 plus does not want to be reduced. It does not want to gain electrons, okay, and go back to the metal. And then MnO2, on the other hand, if that gains electrons, well, you know what, that's pretty favorable. MnO2 is pretty happy with that. Whoops, go back. So this guy would be a better oxidizing agent, or wants to be reduced. And likewise, you can take a look at SN4 plus and sulfur, same business. All right, so that's no problem. But over here on the other side, this time it's the exact opposite. It says circle which species in each pair is a better reducing agent. In other words, wants to be oxidized. Here's my big point here. If you're going to do oxidation, you have to look at that pink sheet backwards. So for instance, if I look at silver and I look at gold, when I look at that sheet, I need to find an exact match on the product side going to reactants, because we're talking about being oxidized. So there's my gold. Okay, so AU being oxidized, losing electrons, going in this direction, will be a negative 1.50. Gold doesn't want to do that. That's why it's called a precious metal. Gold likes being gold. It likes being in its elemental gold and fancy and shiny metal form. Doesn't particularly like losing electrons, okay, to become the ion form. Well, let's see where silver comes out. So that's right here. So notice, Ag plus is not the same thing as Ag. So if we're looking to see how well Ag wants to be oxidized, we have to look at Ag as a solid. Okay, well, if you look at it in the backward direction, Ag going to Ag plus, losing an electron, that would be a negative 0.80. So you change the sign anytime you look at it backwards. All right, well, guess what? Both these metals, both are precious metals. Neither one wants to be oxidized, but who would be a better reducing agent? So we'll pick the one that's less negative. Okay, so silver would win. Again, pause the video, do the next two examples, and make sure you're looking at the table correctly. All right, so we have Br minus and Cl minus. When you look those up, be careful that you are looking up the products. So here's Br minus going to Br2, Cl minus going to Cl2. So switch both those signs. And then the last one was, let's see, what was that one? Let me look here. Oh, aluminum and H2. So aluminum going to aluminum 3 plus versus H2 going to H plus. Okay, so when you compare those values, okay, Br minus would be your winner here, and aluminum is your winner here. Okay, aluminum would much rather be oxidized than H2. Okay, so hopefully you guys are just getting used to using the pink sheet. That's what this part's all about. And you can tell, you can make a decision as if we're talking about reduction, looking at the table in the forward direction, or oxidation, looking at the reaction in the backward direction. Okay, and hopefully we're doing well there. Let's move on. Okay, so now we're putting all this together. So it's basically a three-step process when you're looking at these galvanic or voltaic cells. So 1, you break it into half reactions. 2, you balance the half reactions. And then 3, you calculate the overall E cell. So we got this example. We're looking at this reaction. So you want to decide who's being oxidized, who's being reduced. I already went through and figured out the oxidation numbers. Hopefully you guys remember that. So tin is going from a +2 to a +4. So clearly we're becoming more positive. So that's going to be our oxidation. Now the NO3 minus, remember, it's a -2 on the oxygen, so there's 3 of them, so it's a -6. It's a -1 overall, so that leaves a +5 on this nitrogen, and this guy's a +2. So to go from a +5 to a +2, we have to actually gain electrons. So that's our reduction. For heaven's sakes, one thing has to be oxidized, one thing has to be reduced. So we'll go ahead and break them into their half reactions. This one could be easier. Sn plus 2 going to Sn plus 4, so you have to lose 2 electrons on this side to make the charges equal on both sides. This one, a little trickier, so let's see. We have 3 O's on this side, so the ends are balanced. First 2 balance things besides H or O. Okay, so then, since the ends are balanced, now we balance oxygen. There's 3 O's on this side, there's only 1 on this side. So I'm missing 2 O's. We balance O's with water. This is going back to good old chapter 4 stuff. So now I have 2 plus 1, 3 O's and 3 O's. You balance hydrogen with H+. So let's see, 2 times 2 is 4, so that would be 4 H pluses. All right, last but not least, we have to balance the overall charge on either side with electrons. So this guy, no charge, so this guy has no charge, so 0. But this guy has a +4, so there's 4 positives, and then this minus, so that's looking like a +3. So we have to make the charges equal to each other on both sides. So we would have to add 3 electrons on this side. So 3 negatives and the positive cancel out to 0, so the 0 and the 0 match on both sides. Okay? Now, keep in mind with balancing half reactions that you also have to make sure, the most important thing is make sure that the electrons lost equal the electrons gained. So to do that, we have to multiply through by some multiple to make sure that that happens. So we got 2 electrons versus 3 electrons, so 6 is a common multiple. So multiply all this by 3, and we'll multiply all this by 2. So now we have 6 electrons gained, 6 electrons lost. All right, when it all shakes out, it looks a little something like this. Okay, so I carried the 3 through, and then I carried the 2 through. Okay, notice my 6 electrons lost cancel out with my 6 electrons gained. All right, and then you can add all the reactants together, and you come up with this, and you can add all the products together, and you come up with this. All right, so hopefully that's a little reminder of how balancing redox reactions work. But more importantly is how does that work with the E-cell business? Okay, so this is my oxidation. So if you go back to your pink sheet, you should find that exact oxidation. And remember, oxidation means you got to be reading it in the backward direction. So I'm going to look down here, zinc 2+ going to zinc 4+. So I'm looking at this reaction. So since I'm looking at it backwards, the oxidation potential is going to be this number but opposite sign. So that's how I get a negative 0.15. All right, the other guy is the reduction. So that's the nitrate ion being reduced to NO. So you got to make sure it's an exact match. Okay, in this one I'm reading it as is, so this number is just going to stay 0.96. Alrighty, so the oxidation potential, the reduction potential, and those are measured in volts, by the way. And then to find the overall E cell, okay, that means the electron potential for the whole reaction, just add them together. Okay, so it comes out to 0.81 volts. Okay, the big thing that I hope you got out of the group work activity as well is even though you multiplied this all by 3, did you multiply this by 3? No! Just because you multiplied this all by 2, did you multiply this by 2? No! Okay, these are what's called an intrinsic property or intensive property, which means it is not dependent on the stoichiometry. I like to say that it's sort of the driving force for whether it wants to be oxidized or wants to be reduced. And just because you have more, just because the stoichiometry is one way or another is not going to affect that driving force. Okay, it's a property that's just inherent or part of the soul of that substance. Okay, now I'm getting a little weird. That's okay. All right, take-home message. The positive E cell value, so this is a positive number, indicates that the reaction is spontaneous. Okay, that means it's favorable. And if you're thinking about delta G, yes, we are going there soon. Delta G would be negative. This reaction is going to happen. So the voltage above could be harnessed and used to do something, aka how batteries work. Okay, so you can make a clock run, you can make your iPad run, etc., etc. Okay, so positive E cell values, good, favorable. All right, what else can we do with this? Well, now we get to do some really fun pictures. So the galvanic or voltaic cell, okay, that's like the whole setup of what this experiment would look like. So it involves a spontaneous redox reaction. So E cell has to be positive, meaning the reaction's going to happen. And you can probably guess, yes, we are going to look at non-spontaneous processes. They're called electrolytic cells, and we'll get to those. All right, so batteries are a very common example of galvanic cells, okay, or voltaic cells. So let's go ahead and take a look at one. So this one, we're going to react nickel with copper 2 plus. So the nickel is being oxidized to nickel 2 plus, and the copper 2 plus is being reduced back to the metal. All right, so let's see here, a couple things. One, this is the general setup of a voltaic or galvanic cell. The big thing is that you have two separate containers, okay? If you do it in one container, then you can't harness the energy to do something, okay? So it will work, but you won't be able to do something with it. Okay, the other piece. So I got nickel, that's my nickel metal, and it's going to be immersed in a nickel 2 plus solution. Okay, you have to have both. And we're talking standard conditions, so that's why that's 1 molar. Okay, now the copper. So the copper is the metal, so we call that the electrode. So the nickel's the electrode over here. And then it's immersed in a 1 molar copper solution. So when you set up these galvanic cells, you're going to have both the reactants and the products present in standard form. Okay? Now, if you write out the half reactions, we already talked about the fact that the nickel is being oxidized, losing 2 electrons. And if you look up the E naught value for that, the oxidation potential, it's plus 0.25 because you had to change the sign. Okay? The reduction, the copper 2 plus, it's gaining 2 electrons to make copper solid. Okay? And if you look up the reduction potential, it's 0.34 off the pink sheet. So overall, the E cell for this process is 0.59. So we're actually going to do this in class, but you would, basically connect up what's called a voltmeter, and you would actually measure a voltage of 0.59 volts. Okay, and depending on what two metals or what your conditions are, you can change, you'll get different voltages. Okay, a couple other details. Let's see. First of all, reduction takes place at the cathode. Okay, so going back, you want to definitely label this as the cathode. Now, I always remember the red cat. I'm going to tell you what, it does not matter what the circumstances, at the cathode is where reduction will take place. Okay, so that's where gaining electrons will happen. And then on the other side, we call it the anode. So I just remember NOx, right? The vowels go together, and a red cat. Okay, so that's the first detail. So in this case, for the cathode, the copper 2 plus is gaining electrons to produce copper metal. Oxidation takes place at the anode, so anox. All right, the nickel metal is being oxidized, is losing electrons to produce nickel 2 plus. So that's in a nutshell the two half reactions. Okay, now this is a big one. What about the mass? So the electrode is the solid material, right? What's going to happen to the mass of the nickel electrode? So let's go back here. Now, if you think about it, the nickel is losing electrons to produce nickel 2 plus. So some of these nickel solid particles are actually going to leave and become part of the solution and become part of the nickel 2 plus down here. So what's going to happen to the mass of this actual solid electrode? Well, I hope you're thinking that it's going to get lighter, okay, because you're losing mass off the electrode. Likewise, you can probably guess over here. The copper 2 plus from solution is actually gaining electrons to produce copper metal. So this guy is actually going to get heavier because we're going to add and add and add more copper metal to the electrode. All right, so the nickel electrode would get lighter, excuse my terrible penmanship, and the copper electrode would get heavier. Okay, explain why? Well, rewind the video if you need to. Okay, hopefully you can explain why. Okay, now the electron flow. So let's go back. How are the electrons moving? Okay, so keep in mind, where are they being lost from? So the nickel's losing the electrons, right? Okay, and then so the electrons are being lost over here, and they're traveling through this wire, okay, and through the voltmeter while we're getting the reading, okay, and the electrons are traveling, and they're just kind of hanging out here, and then the copper 2 plus picks them up to become copper metal. So the electrons are traveling from the anode to the cathode. All right, the electron flow, electrons move from the anode to the cathode. Okay, and there's this little tip in like size -5 font, cathode, that says electrons know their alphabet, right? You'd go from A to C according to the alphabet. So the anode to the cathode. All right, well that's fun. Now, as I mentioned, in a galvanic or voltaic cell, to actually create electrical energy, to actually get a reading on that voltmeter, that's why the half reactions have to take place in 2 separate containers. Okay, if you didn't do that, you know, if they were just in one container, the electrons would just transfer straight across and the redox reaction would still happen, but you wouldn't be really harnessing that electron energy as electricity. Okay, so if you actually want to do something with the the electricity produced here, that's why you got to keep it in 2 separate containers. Okay. Finally, oh yes, whew, this is big. Okay, basically, as drawn, this galvanic cell would not work. Okay, you'd get no voltage. Okay, why? Because I want you to think about it. You know, nickel is going to turn to nickel 2 plus. Well, you're going to keep increasing the positive charge and increasing the positive charge. That's a problem. Okay, because the world at large says that things overall have to be neutral. You know, you can't have just positive charges swimming around without the negative counterpart. Okay, and same thing over here. These 2 plus are going to grab the electrons and they're going to be leaving solutions. So you're going to have this net negative. Okay, that's just not allowed. So somehow we have to sort of manage those charges. So that's where dun, 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 the salt bridge comes in. Phew, plop. Okay, so please draw that in. Okay, because you absolutely have to have a salt bridge if you want this all to work. So here's a salt bridge. Now I'll tell you, my favorite salt bridge, I know this is going to be kind of gross, is sometimes I just use like a cut up hot dog. Okay, hot dogs are great because they're kind of like gushy and flexible and you can bend them. But most importantly is that they have cations and anions in them. So the most common salt bridge is usually made up of like potassium nitrate. So you got potassium ions and you got nitrate ions available. Hot dogs are full of nitrates, okay, because it's a preservative. All right, so you got this salt bridge, and you know what? These ions that are in the salt bridge, they can go wherever they're needed to sort of balance out the charge. Okay, so like we said, let's see, we got a high amount of positive charge over here because the nickel is going to nickel 2 plus. We have too much positive charge. So what ion is going to go over there to balance it? Okay, well, to balance out the too much positive charge, we're going to send over the nitrate. Okay, so the nitrate's going to start heading over there. Over here, kind of the opposite little situation here. We're losing 2 plus, so we have too much negative. So we're going to send the potassium over there, kind of balance it out. So salt bridge is really kind of an easy thing. It's very important. It's easily forgotten, but it does serve a really important role. So salt bridge, sometimes they call it a U-tube. You know, it's like the fancy term for a hot dog, okay? So it's whatever. Some material filled with a non-reactive electrolytic. Electrolytic means ions, okay, like KCl or KNO3. Porous disc, you know, that's just another way to kind of let the electrons sort of transfer through. So again, what's the purpose? To balance out the positive and the negative ion charges in each beaker. All right. So yes, so we use the potassium nitrate salt bridge. Okay, so how does it work one more time? The potassium ions, in the example we're using, so we'll say the cation, would migrate towards which side? The cathode or the anodes? Cathode or the anode side? The K plus went to the cathode. Okay, so the potassium ions would migrate towards the cathode. Cation. Wow! Cation would migrate towards the cathode. Seeing a little connection there? And the nitrate, the anion, would migrate towards the, whoops, that should be anode. So keep your vowels together, keep your consonants together. It's just a little device to help you remember, but keep in mind, most importantly, you got to remember why the cation goes towards the cathode and the anion goes towards the anode. It's very difficult to say. Last but not least, there's this fancy little notation that we can use to express a galvanic or voltaic cell or any cell. You always list oxidation first, followed by reduction. Okay, so nickel got oxidized to nickel 2 plus. Good? This line indicates if there's a phase change. So we went from solid nickel to aqueous nickel. If they were both aqueous, for instance, we just separated with a comma. Okay? This is your salt bridge. Okay, so that's when you're going from oxidation to reduction. So copper 2 plus got reduced gained electrons to go to copper metal. Okay? These can get a little bit more complicated, but that's basically what you need to know for now. All right, I hope this filled in some of the gaps about what electrochemistry is all about. Do not worry about the rest. We're going to do this fun stuff in class. If you haven't read 18.2 to 18.4, you definitely want to get that read sometime soon. All right, thank you very much for listening, and talk to you later.